Um, so yeah, okay. So summarize. We got today 6.4, the Gram-Schmidt process and the QR factorization. They're kind of intimately related because the QR factorization relies on the orthonormalization of vectors. And so remember, the idea is to create uh, another set of vectors that are orthonormal, that are perpendicular and of unit length from the unoriginal set of vectors that we have. We'll try to solve for this, try to look at pictures, and and then be able uh, to find that orthonormal set, and then come up with a matrix in the QR factorization. We're going to use that orthonormal set, and then we're going to be able to. This is going to be our second way to factor a matrix. Remember, the first one is the LU. Remember the LU? Oh yeah, you remember the LU. It was on the test. So the LU decomposition, and then next time or today we'll briefly touch on the QR, and then next couple of weeks we're gonna do our final decomposition of matrices called the SVD, single value decomposition. All right, let's talk about the Gram-Schmidt process. And the idea behind this is that all the things that we've been doing in section 6.1, 6.2, and 6.3 is kind of a buildup to this. And so the idea here is that if you're able to kind of understand the lectures the last couple of times and then watch the video, a lot of these components from the Gram-Schmidt process should look very, very familiar. So here's a process. The idea is again, to create an orthonormal set given a current set that may or may not be orthonormal. So if you have a set of bases that may or may not be orthogonal and unit length that spans a particular subspace of Rn, then we can define a set of new vectors. So we have p vectors here currently. We can define another set of p vectors, and those the vectors v1 through vp are going to end up being an orthonormal basis for us. Just yeah, renaming a vector. Oh, yeah, yeah, yeah. Yes, yes, yes. So we're looking at this. If you look at that gray dot, I was going to call it ship. It's a ship. If you look at that gray ship has three vectors going out of it, right? And so that would be, let's say that represents my velocity, acceleration, and some other third vector that makes it linearly independent. Yes. So that's what I start off with. And what I want to do is to create another set of vectors that would span the same space. In this case, it's all of R3. So I want to be able to span the space, but those new vectors that I want should be mutually orthogonal and unit length. Okay, so that's what we're going to try to do. Chris? Yes. Well, that's kind of like what Nate's comment was earlier. So the idea is that if you have an orthonormal basis, then you're just counting by units of one uh, in the three directions, and the three directions are all perpendicular. So it's like having an ijk vector, but having your own ijk vector in your own chip pointing in your own direction. And the ijk vectors are generally easier to deal with than random length and random angled vectors that span the same space. So
I would assume if you know, say, the coordinates of your target,
yeah.
you take your three vectors
Right.
whatever.
Right. You could probably do that too, but having things in as mutually perpendicular and unit length would make some of the calculations easier. Yeah. No, not necessarily. Like these three vectors coming out of that gray ship are not necessarily orthogonal, but they're linearly independent. Okay. Any other questions? All right. So the idea behind this is to create an orthonormal set. So first, we're going to create an orthogonal set of vectors. And the orthogonal set of vectors, after we create the orthogonal set of vectors, then we'll normalize each one, and then that's our plan. So to create an orthogonal set of vectors, we're going to start off with the first vector being the same vector as it is, yeah, as pointing. We're going to shrink this into unit length or extend it to unit length, whatever the case might be. We're going to make this of unit length a little bit later on. Okay. So, but the first vector is just the first vector, nothing to that. Now the second vector, we'll use the projection. So Brian had a question earlier about calling this a projection versus the perpendicular vector that's a subtraction. So the projection of v2, the second vector, onto the first vector v1 is this highlighted set over here, which is what we've been dealing with. Right? We're projecting it onto, in this case, just another vector. And then if you subtract it, you get the perpendicular vector. So this is what we're going to do. We're going to subtract x2 minus what we found in the projection. Okay? So that part is easy enough to think about. That's the stuff that we thought about in Calc 3 for those people that have had Calc 3. It's just a projection onto one vector. Now I have two vectors, v1 and v2. They're perpendicular to each other already. So now v1 and v2 is two-dimensional space. They span the same plane as x1 and x2. So I can use v1 and v2 or x1 and x2. But now what I'm going to do is I'm going to now this technically should be a plus, and if we think about it this way, we'll put a parentheses around there and make this into a plus, and then put the other parentheses out here. So this thing that's in parentheses is a projection of x3 onto the two-dimensional space that's spanned by x1 and x2, which is the same two-dimensional space that's spanned by v1 and v2. So that's that vector there. And now if you subtract your current vector x3 from that projection, you're going to get your third perpendicular to the other two, your third vector that is now all mutually orthogonal. Jesse. Yes. So this is x1. This is x1, x2. This is x1, x2, x3, right? Now, x1 and x2, and it's the same plane that's spanned by v1 and v2. This thing in parentheses is the projection of x3 onto that plane. And now when we do the subtraction, this vector that we get would be x3 minus that projected vector, and now that is perpendicular to x1 and x2, or v1 and v2. Okay? Now, to go further, we can't picture it anymore because it's in fourth dimension, so we'll just leave it like that. But that's the idea, you keep going. So a fourth dimensional vector, you would project that onto three-dimensional space, and then you subtract it, and then et cetera, et cetera. So you have a piece of p minus 1 dimensional space, and then you have a pth vector, and then you would project it onto that p minus 1 dimensional space, and then subtract, and then now you have another vector that's perpendicular. It's all kind of cool, isn't it? Well, okay. All right. So now that you have v1, v2, and all the way up to v sub p, that spans the same space as the original set of vectors, and it's all orthogonal. The only thing left to do is make it all unit length. Then you're done. Chris. Yes, because if it's not linearly independent, then when you project it and you subtract it, it's going to be in the same space. And then, all right, so here's my example. These are the same vectors that's going to be in that chip that I'm flying, and I'm going to try to find an orthogonal set of bases. Okay, so let's take a look. I'll label them x1, x2, and x3, and then I will attempt to find v1, v2, and v3, and then normalize everything to u1, u2, and u3. So x1, x2, x3. So my x1, or my v1, is going to be x1, which is equal to this. My v2 is going to be x2 minus, I don't know why I'm writing this over again. But it looks like I need the dot product of v1 and x2. So x2 was negative 101 minus the dot product of x2 and v1. That's essentially the dot product of x2 and x1, right? Because v1 is x1. So I have a 1 times 1 is 1, 0, positive 2, 1 is 3, right? And then now I want v, wait. Oh yeah, v1 dotted with itself. So that's x1 dotted with itself. 1, 4, and 4, 9, 9, right? Square root of that. Let's put square root of 9, which is equal to 3. And then times v1 minus 1 to negative 2. What is this? This is this is 1, right? So I have minus 1 minus negative 1, that's 0. 0 minus 2, and 1 minus negative 2, 3, right? Is that right? No. 1 minus 1 minus negative 2, right? Yes. Forgot my negative. Okay, so what was that again? 0, negative 2, negative 1, positive 1. Yes. Oh. No, yeah, you're right. Thank you. I wasn't supposed to square root it. I was thinking about the magnitude, but according to the formula, it's just a dot product. Sorry about that. That makes this into a 3. 1/3, right? Let's try that again. So what's this equal to again? -1 plus 1/3. 4/3. I really feel like pulling out MATLAB. -4/3, right? 0 minus 2/3, and -1 minus 2/3. -1/3. That's hard. Okay, that's my V. Boy, this doesn't. My V3 is going to be hard. First one's -2/3. There's people observing me. I can't add. All right, V3. Thanks, Chris. All right. So V3, what we're going to need is x3 minus. So I'm going to use my slightly modified formula with the parentheses and just add a whole bunch. I don't know if that's going to make things any easier. But it looks like this is going to be x3 times dotted with v1, v1 dotted with itself times v1, and then x3 dotted with v2, the new v2 that I found, v2 dotted with v2. And really, we could have used x2 instead of v2 because it's all on the same plane anyways. But let's just make things a little bit more complicated for ourselves. So we have x3, which is -2, 1, -1. And then now let's do some dot products here. We're doing x3 times v1, which is x1. So I see that as a 2 plus 2 plus 2, 6. And then v1 with itself, we got that to be 9 last time, times v1. And then the second one is x3 and v2. So this is x3 right here, and this is v2 that we found. So that's negative, negative, so it's positive 4/3 minus 2/3 plus 1/3. Just one? Negative 1/3. So positive 4/3. Yeah. And then minus 2/3. And then we add 1/3. So that's 3/3, which is 1, right? And then the magnitude of, or the dot of V2 with itself. So let's take the dot product of this. 4, 8, 9, 9 over 9. So that's 1 again, isn't it? So the dot product of V2 with itself. Right? Negative 2/3, negative 2/3, negative 1/3. Does the dot product equal to 1? So that means this is already a unit length. So that's good. And then we're going to multiply that by negative 2/3, negative 2/3, negative 1/3. So now we want to find all this. Oh boy. Negative 2/3, 1/3, and what? 2/3. Wow. Well, if nobody's going to object, I'll go with that. All right. So, is this unit length also? It's already a unit vector, huh? It's what? Yeah, but when we actually dot it, we get one. So that would be great if it is. And so to find our unit vector set, our U1 is going to be just this thing divided by its magnitude. So the magnitude, not the magnitude, yeah, the magnitude. So 4, 4, and 1 is 9. Square root of 9 is 3. So U1 is going to be negative 1/3, 2/3, negative 2/3. U2 is V2 because it's already a unit vector. Negative 2/3, negative 2/3, negative 1/3. And U3 is already a unit vector also, negative 2/3, 1/3, 2/3. Now, when you guys find your V1, V2, V3, it may not yet be unit vectors, so you have to be aware of that. You have to make sure that you make it into a unit vector to make an orthonormal set. All right, let's see. Yeah. So I have this set up already where my t vector is kind of like my unit vector. So the t, the first vector is going to be the red vector, which is the longest vector there. I don't know if you can see that it's red, but it's red. So if I make this into minus 1/3, 2/3, and minus 2/3, you see that I get another vector of unit length going in the same direction as my x1 vector. You see that? Do you see my new vector? The green vector? Right? So now let's see what happens when I include my second vector. My second vector is minus 2/3. Minus 2/3. Oh, come on. And minus 1/3. Now, I got another vector there. If you look at it carefully, it's perpendicular, but not only that, it's on the same plane as the span of my first two vectors. Can you see it? My first two vectors are the red vector and the blue vector. And if you look at it, these two thicker vectors look like they're perpendicular, but not only that, it's also on the same plane as the blue vector, which is the second vector. Okay, you have to wait till it goes in that right angle to, not a right angle, but the correct angle to get that view. Now let's get that third vector. Now there's two possible ways for the third vector to go, right? Because I have two perpendicular vectors in R3. I can go, one or the other way. And so what to watch out for is that third vector that's not on the plane is going a little bit off of the plane. It's going to go in the same direction as that off of the plane vector. So our third vector for our orthonormal set is minus 2/3, 1/3, and 2/3. So there are my three orthonormal vectors. One of them going in the exact same direction as my first vector. The other one would be the same plane as my other two vectors. And then the third one is going to be in the direction of my third vector. Okay? That's my target. I'm going to hit that. All right, so what is my target? I think my target is, it's a -2, 4, 3. So, just to get you guys ready, and I probably should do this in like 2 minutes, just to get you ready to play your game in your worksheet, is that if I have a target, what I want to do is I want to express a vector as a linear combination of the new basis vectors that I found. Okay? Now, to do this, well, first of all, I need to know what my vector is. So let's say my new vector, so I want to target that vector. So I want to create a vector from my position to that blue vector. And so my position is P, my position is 1, 1, 1, and then my new vector is -2, 4, 3. And I just made that up, okay? What did I say? -2, 4, 3. So if I subtract this, I'm going to get -3, 3, 2. So now, without really thinking, yeah. Oh, because I want a vector from my ship to that point. And that's why I'm subtracting it. That's just for this particular worksheet. And so what I want to do is I want to hit that that vector and have a new vector. And so basically what I want us to focus on is this equation. So we can construct a matrix, right? And then just solve for this as if this was an AX. So if we make a matrix U, I'm out of room. U would have U1, U2, U3 as the column vectors. And then, so U times the C vector, C1, C2, C3, should equal to this other vector that we have, -3, 3, and 2. This is like the AX equals B problem, right? So what I could do is I can solve for C, C1, C2, C3, but I need the inverse of U. Now U is an orthogonal matrix. Remember orthogonal matrices? What's the inverse of an orthogonal matrix? What? What? The transpose. So all we have to do is find the transpose, which is easy because we have these matrices, and then apply it to this, right? So our U matrix is these things, the transpose is whatever the transpose is, all right? So I need to do it. Okay, I got permission. All right, so let's say my U vector U1 equals negative 1/3, 2/3, negative 2/3. My U2 vector is negative 2/3 minus 2/3 minus 1/3. And these are column vectors, yeah? And then my last one, U3, is equal to minus 2/3, 1/3, positive 2/3. And then my Y vector is, what was my Y vector again? Negative 3, 3, and 2. Okay, so I'll create my U vector, or my U matrix is equal to U1, U2, U3. And then I'll take the transpose of that. And then I'll apply it to my Y vector. So 1.667, negative 0.667, 4.333. All right. Let's see if this works. So 1.6667 minus 0.6667 and 4.333. Now this is cool. Here we go. Bam! All right. So this is what you guys are going to do. I'm going to give you a number, and you guys are going to pair up. So you guys are going to first work with pairs. After that, you guys are going to start working with other people. How many people in this class? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, going more. 15. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. You're number 1. So find the people the same number as you. I have only 15 copies of this. So, oh, okay, wait, before you start, think about this. There's 4 problems here. I want you to take your number, divide it by 4, and find the remainder. The model. Right? So, whatever that number is, the remainder. Well, did you guys do that in your head? Okay, take your number, divide it by 4, and find the remainder.
there's no remainder, the remainder is 0. Okay? So, you will find your partner, and you have your mod in your head. Okay? If your mod is 1, if you have remainder 1, your ship number 1. If your mod is 2, your remainder is 2, your ship number 3. If your mod is 0, you're ship number 4. Okay? So you have a position, you have velocity, acceleration, and a third vector, and then you need to create an orthogonal basis out of the 3 vectors, not your position.
All right, find your partners. You're finding the same number as you for now. No, you're finding the same number as you. Yes.
By the way, you're welcome to use MATLAB, Ultra Alpha if you want, your calculators, and make some computations here.
All right.
Can I have your attention once you guys have the sheet? So, the orthogonal basis that you want comes from the velocity, acceleration, and the third vector. Okay? The orthogonal basis that you want will come from the velocity, acceleration, and the third vector. Alright? So, the first part is to find your orthogonal basis. And that comes from the 3 vectors down here, the velocity, acceleration, and third vector. Do you want something to compute the basis? Well, I want you to compute the basis for here. And then the next task is that you want to identify your target. So your target, if you're ship number 2, you're going to try to hit ship number 3. Alright? So your target would be the position for ship number 3. What is it relative to you? So you need to subtract those 2 vectors. And that's the vector that's going to shoot. That's the vector that's going to shoot from your ship to the other ship. You want the answer in terms of the basis function. I want the answer in terms of the basis vectors U1, U2, and U3, and these should be the constants that you're going to find.
My position is subtract the other position on the other.
The other position is subtract your position. One more question: should we make sure that we're decisive? I only care about the answer.